Hi kids, welcome to the fourth video on sound from this waves unit. The essential question is, what is sound and how do the wave properties that we've learned about impact the sounds that we hear? So let's start off by kind of defining what sound is. Sound is a series of pressure pulses in the air, or it could be through a different medium, because you can hear in other media as well. And those pressure pulses hit your ear. We're going to talk one of these days about how we hear, what kind of features in our ear contribute to hearing the sounds that we hear. But you should just generically know that our ear can detect some sounds, not all, right? Different animals can hear sounds that we can't hear. That doesn't mean they're not sound, just they're not ones we can hear. And that our brain can categorize or interpret these sounds different ways. It's really useful to be able to not just determine that something is making a sound, but learn from the sound. Obviously, we can tell speech, or we can tell volume, we can tell pitch. Those kinds of things are all things that our brain has learned how to categorize. Of all the wave properties that you learned about in previous slideshows, there are only two that we can actually detect and categorize, and those are the frequency and the amplitude. So the frequency of the sound is how often those wave pulses are hitting your ear. You have these little hairs inside your ear that will jiggle back and forth, and every time they jiggle back and forth, they send a little electrical signal to your brain. So your brain can detect how often those things are jiggling and therefore determine the frequency of the wave. We can also detect the amplitude, which is the energy in the wave, which is basically how big the jiggle is. So did those ear hairs wave a lot or a little? And your brain can also get that signal from the ear hairs and can determine the amplitude of the wave. So the first wave variable that we can detect and interpret is sound frequency. Humans interpret different frequencies as the pitch of the sound. So if you hear a low frequency sound, it's going to sound like a low pitch, low. So that's a wave source that is not vibrating very many times every second. The other end of the spectrum is a high frequency sound, which makes a high pitch, high. And that sound that you just heard reflects the fact that that wave is vibrating very quickly or many times every second. The typical range for human hearing is between 20 and 20,000 hertz. So the sounds that your ear is capable of detecting are vibrating between 20 times a second and 20,000 times a second, which is really fast. Your vocal cords can't make all of those sounds, but it's kind of amazing to think that you have a muscle in your body that can vibrate thousands of times every second, and does that when you are speaking or making another noise. The second wave variable that our ears can detect is the amplitude. And as I mentioned, the amplitude is a reflection of the energy of the wave. So if you receive a sound wave with more amplitude, that means that it's like a stronger, bigger pressure pulse. And our brain is going to interpret that as a louder sound. So low amplitude sound, high amplitude sound. So there are other wave variables as well. These cannot be determined by direct observations from our ears into our brain. However, we can measure them with other scientific instruments. So for example, the wave propagation type, the speed of the wave, and the wavelength all can be measured, although they're not something that you could tell when you're listening to a sound. As I mentioned before, sound waves are pressure pulses, which means that they're going to be longitudinal waves. That picture shows sort of an example of what that might look like in the medium of the air. So there's places where the air has really dense, high pressure, and then other places where it's spread out. Sound waves can travel through almost any medium. As you know, you mostly hear sound through air, but you also could hear it underwater. If you put your ear up against metal or cement, you can also hear sound through it. So almost any medium can actually transmit these longitudinal pressure pulses. However, even though sound can travel through all these materials, the speed of the wave is different in each material. As we've talked about, the speed of a wave always depends on the medium, and sound is no different. It turns out that sound actually moves fastest through solid materials because it's a pressure pulse. If you imagine pushing on one side of that ice cube, that push would be transmitted very quickly to the other side because we have these really strong bonds between all the atoms in a solid material. Liquid, it would take longer for that pressure pulse to move from one side to the other, right? If you splash on one side of the liquid, it takes a little bit of time before that splash gets to the other side of the cup. And in gas, if you push a gas, it takes even longer to get to the other side because those molecules have to move quite a ways before they bump into another molecule. So sound goes fastest through solids, goes kind of a medium speed through liquids, and it is the slowest through gases. So the wavelength of sound is not something that we can detect. We can't tell for certain what the wavelength of a sound going in our ear is. We don't have any means of measuring that. But in general, audible wavelengths are between centimeters and meters long. Since the wavelength depends on velocity and frequency, if you move to a different medium, the same wave is going to have different wavelengths, but your ear can't actually tell the difference. So, for a summary, please revisit the essential question, which is what is sound and how did the wave properties impact the sounds that we hear? And we'll talk a lot more about ears and how sound works in class. Thanks.